Yes, Mehak, you can ask.
Uh, so, like, how do you know if the kernel is separable or not?
I think there is some echo coming from your side. Can you?
I'm audible now.
Sorry, Mehak, there is still a echo coming from your side. Can you post it in the chat?
Yes, sir. So is it better now?
Yes, this is better.
Yeah. So I wanted to ask you, how do you know if a kernel is separable or not?
Okay, I lost you again. Can you say it again? What was your
Uh,
doubt?
yes, sir. So how do you know if a kernel is separable or not?
Ah, so you is it in week one or week two? Week one, right?
Week two.
Week two. Okay. Give me 1 minute. I will open the slides. It is given in the slides, right?
Yes, sir.
Give me 1 minute. I am opening the slides. So it is something to do with the eigenvalue. I think if there is only one non-zero eigenvalue, then you can say that your kernel is separating. Else it is not. Something like that is there. So it's basically about the rank one matrix. Like you do you know what is a rank one matrix?
No, sir.
Sorry,
No, sir.
you don't know rank one matrix. You
Okay,
don't know
rank one.
rank of a matrix.
Yes, sir.
So if you see that I am opening. Wait 1 second. Okay, so let me open the portal and go from there. 65439. Do you know in the slides which part it is? Do you remember
Part
that?
two.
Part 2 is it? I think part 2. I'm opening the part 2. It's not in part 2. Just give me 1 minute, okay?
Okay, sir.
It's in week 1 actually, it's not in week 2.
1.5 it is.
Okay? Open that. Can you see my screen?
Yes, sir.
Yeah. So it is something like this. If you can represent a kernel as an outer product of two matrices, two vectors, then that matrix or that kernel is called a separable kernel, right? That is the definition.
Yes, sir.
So now, basically, there are multiple ways to find it. Simple way is because we can represent this kernel matrix as a outer product. This kernel will have a rank 1. Okay,
Yes, sir.
because you are taking an outer product, only one of the rows or columns will be independent. So here for this particular example, given this kernel matrix 1 to 1, 2, 4, 2 and 1 to 1, how many independent rows are there? Do you know the difference between dependence,
Oh,
independent? You must have learned that in linear algebra, right?
yes,
Independent
sir.
rows and columns of a matrix.
Yes, sir.
Yeah, so here basically you can represent any two rows. Like the second row is just a multiple of first row, and same like third row is just a repetition of the first row, right? Same goes for columns, right?
Yes.
So we can clearly see here that only one independent row or column exists for this matrix. Yes.
Yes.
Yeah.
Yes.
So that is the reason why you can represent it as a outer product kernel, or it goes other way around. Now you see how, if you see how you do outer product, VH transpose, what you are doing is you are taking a column vector and a row vector and multiplying the first row of that row vector by the first element of column vector, then second element, then third element, right? So you are just repeating the row as a multiple of elements of your column vector, the first vector, as a vector of v, right? That is what you are doing. Let me open a document and show it to you. So, can you see my screen?
Yes, sir.
Yes. So we say that a kernel can be, if we can represent a kernel as a VH transpose, then it's a separable kernel, right? So now if you see, let's say V is our matrix, it's a column matrix, two, one. Okay. I'm writing it as a row transpose of a row matrix, and let's say our H is something like 2 comma, okay, something like 1 to 1 only. Let's take it that. So now, can you tell me what will be the first row of the matrix K? Can you tell me? You will
One
take
to one.
you will take this vector, multiply it with 1. You will get 1 to 1, right?
Yes.
Same way, you will take this row vector and multiply it with 2. So now you get 2, 4, 2, right? 2, 4, 2. And again you will take the 1 to 1 vector and multiply it with 1. You will get 1 to 1, right?
Yes, sir.
So now you can see that only one of the row or the column of this matrix K will be independent, right? Because all other are combination of that vector only, this vector only,
Hmm.
right? We can have anything here. We can have anything here. 4, 5, 6, right? So first thing you will get is 4 comma 5 comma 4 comma 5 comma 6. Second one you will get is 8 comma 10 comma 12, right? And again you will get 4, 5, 6. 4, 5, 6. Right? So now we can clearly see that only this row is independent, or this row is independent, because other two can be found out using this row. Other two are linear combination of this, right?
Yes.
So the rank of this matrix is 1. Yes, this
Correct.
kernel rank is 1. Now, the way to find, given a kernel matrix, the way to find whether given kernel is linearly separable or not is to find rank is 1. Now, how you find whether the rank is 1, it is up to you. In the slides, if you see, it is given, yeah, this slide 40. Okay, if you look at the singular value decomposition, only one singular value is non-zero. That also tells you, singular value means square root of your eigenvalue, right? So that also gives you the way to find rank. That only one eigenvalue is non-zero. That means it's rank 1 matrix, and you can say that okay, this kernel is separable. Is that fine?
Yes, sir.
So it is completely up to you how you want to find the rank. In the slides, one way is given, which allows you to find the kernels also. So kernels just becomes linear combinations of, or the H and V matrix are the kernels, U1 and V1, some scaled version of those.
Here, U1 is basically H1, right?
Sorry,
Here, U1 is basically H1, right?
that no, U1 is not H1. Scaled version of U1 is H1.
Okay.
You, so you have the two kernels, like right? You can represent it as V and H.
Yes, sir.
So V, they are calling a horizontal kernel, which is your first one, root sigma 1 U1, and root sigma 1 V1 is they are calling horizontal kernel. So when they are representing something as a transpose, any vector. So I don't know whether you know this or not. Any vector written like V without any transpose or anything, you should assume that it is a column vector. And any vector written in this transpose form is a row vector. So by default, a vector is a column vector. So that is why they are calling horizontal and vertical and horizontal, something like that. Okay.
So basically, the first one is V and the second one is H.
Yes.
So, could you also explain shift theorem?
Sorry.
Shift. Hello.
Yeah. I can't hear you. What you are
Uh,
trying to say?
shift in week two.
Can you write it in the chat? I think your voice is very swift. Okay. You are asking about Swift. Okay. Let me open the slide for Swift also. Swift is in week two. Let's see. So, do you remember which is part
Week
it is
two,
in?
fourth part. Week two, fourth part.
It's in week.
Sorry,
Week two, part four.
part four. Okay,
Yeah.
sharing it. Right. Any specific doubts in Swift?
Like, could you summarize like how it works basically?
So yeah, these are the basic steps, right? First, you have to find the interesting points which are invariant to scale and orientation using some method. Here, DOG is one of the method. Okay, then you localize those key points. You basically determine the location. Then using the local image gradient, you find the orientation of each point. So it's every step you are doing, and once you got that, you extract the local gradient around those key points to as your features basically. So each step has some, like, for the first point where you determine the interesting points, you use different Gaussian methods to find. Okay, different Gaussian means you are just changing the variance, you're scaling the variance or the standard deviation.
So when we change variance, does the size of the kernel increase? Like when we have high variance, the kernel becomes bigger in size.
Yes. No, no. So that is what you are trying to do. You are trying to find those key points which are scale invariant. So you can see here that in the when you increase the this thing sigma, just sigma, right? Size is not changing here, right? Here also, even
No,
if you
size of the
size of the
filter, the Gaussian filter that we're applying to the
size of
image.
the filter. No, I mean you are increasing the sigma, just sigma, the variance.
When you increase sigma,
Yeah,
how
I
does the
mean
filter change?
you are increasing the variance. That means you can cover much more area. Yeah, you are right in that sense. Right? Yes, you are increasing the spread, right?
Yes, and that means the image becomes smaller, the output image will become smaller as a result of that.
Image becomes smaller.
Yes, because the corner size has become bigger.
Okay.
I think the image doesn't become smaller. I think the distribution that we take for the Gaussian filter is going to be more widespread, right?
Yeah, it can cover more area. You can say.
Which means it's probably going to blur or whatever, right? It's going to distribute that little more instead of centering it around the middle pixel.
But if we don't use any padding, then it will actually reduce the size of the image.
No, no. So you are thinking it from the convolution perspective. You just think of it from the like you want to detect the interesting points, which are scale invariant. Now, how do you do that?
So, what is meant by interesting points here? Are
Sorry.
we looking? What is meant by interesting points here? Does it mean that
So
points which have? Yes, sir.
yeah, yeah.
Hello.
Tell me.
Does it mean points which have high intensity change, like edges or texture?
It can be texture. It can be change in intensity also. That depends, right? So that is what you want to get from given an image. You want to find the features, right? So the first step of shift is that you want to find those features which are scale invariant. So you need an example. Okay, just give me 1 minute. I'll show you one example. So this is what you are trying to do.
So can it, hello?
Yes.
So can it also detect patches where
So
it's just
can you
plain
see
color?
here?
Yes,
Sorry.
sir. Yes, sir.
Yeah, yeah, yeah. Tell me.
So can it also detect like simple like plain colors, like only white color patch or something? Like would that also be considered a key point here?
You are talking about Swift.
Yes, sir.
So it can detect, like it depends on the kind of image you are taking. It you can use grayscale image also. That is not a problem. But if you see here, this is what is happening. So what you are trying to do is you are trying to create this scale space. You take the original image and generate progressively blurred out image using a Gaussian filter. Okay. So this is what you are trying to do. At the first step. Why we need to do this? Because in your image, everything is not at the same scale. Like for example, what they have given here, maybe you can also go through this. I'll share the link. What they say is all the objects in your image are not at the same scale. Like your tree is very big as compared to a leaf. So you want the features so that they are invariant to that scale, invariant to that scaling.
Correct.
So one way to do that is using the Gaussians of different variants. Basically, you are trying to do is you are changing the scale of the Gaussian. Sigma is the scaling parameter for amount of blur. As we increase sigma, more and more details are removed from the image, that is more blur. So basically, as you increase the scale, you can basically see this image as we increase as they have increased the scale to 256, you can see only tree is visible in this image. I mean, it's not that visible, but we can only identify it as something like a tree, right?
Correct.
So that is how, and I think you do some sort of difference between this uh, different scales of this Gaussian filter to get your scales invariant feature. Then you basically go to the next step, which is your this thing, the localization of the
So,
camera.
so why does blurring help?
Sorry.
So why does blurring help in this process?
So
Like
that
what's
is
the
what,
purpose?
right? What you are trying to do is you are trying to get the all, like basically you don't want your features which are changing because of scaling, right?
Correct.
So that is why it's not just blurring. I think it's not just blurring. You are trying to, one second, it is not just blurring. Yeah. So see here, it is not just blurring. You are calculating the difference, right? Difference of Gaussians.
Correct.
So basically, what you are trying to do is you are applying a scale. Like say you take the scale 1 and scale 256 and you calculate the difference. You get those features which are invariant to this scaling, right? Because those features which are not invariant will get removed because of the difference.
Correct. Only those features will remain which do not get affected by this.
Yes.
Yes.
So I mean, this is what I was showing is not just the only step for this first part. You are calculating the differences of Gaussians. right?
Yes, sir.
See here, your difference of Gaussian for x and y and sigma is I had xy sigma and I had xy k sigma, where you are calculating, you are taking your image and applying the Gaussian filter with whatever sigma or k sigma, right? So that is what you are doing. You are basically trying to remove the features which are uh, variant to the scaling, which varies because of
Correct.
scaling.
And we have to subtract the next one. Basically, I cannot subtract the first output with the fifth output. Like I have to
Yeah.
subtract
The
first.
second step is localization. So once you have determined the key interesting points, now you need to know their location in the image, right? That is what the
Correct.
location called, localization called. So now you need to know the location and method, the algorithm which is the method they are using is based on stability. Now, what is stability? Let me go to that slide. Yeah, so it's based on some Taylor series expansion and one second. Yeah, this is what you are trying to do basically here. So you are trying to find the extrema. Let's say in a sampled image, the red ones are true extrema and blue one are the detected extrema. So you can basically you can represent any function, and images are also can be represented. I mean, you must be remembering it from the previous lectures that you are representing your image as a function here, right?
Yes, sir.
Okay, so we can do a Taylor series extension for any function. We can do a Taylor series expansion for any function around the small change, right?
Yes, sir.
So this is just the Taylor series expansion. You write it at the initial point s naught, the function at s naught. You take the derivative at s naught, change in whatever is your change, and you take the second derivative at s transpose. Basically, Taylor series expansion up to second order. Okay. Now the location of extrema is determined by the taking the derivative of this function d of s naught plus delta s with respect to s. So when you take the derivative of this function with respect to s, your first term is gone, right?
Yes,
There
sir.
is no s in that.
So,
Only,
D gives the intensity value at position x comma y. Is it?
sorry,
So D gives you the intensity value at position x comma y. Is it?
I think you will see here you have x naught, y naught, and sigma naught. So three things are there, right? So that sigma is coming from your previous step, I think.
Is it sigma? Is it referring to which output we've got, like sigma or k square sigma?
Sorry.
Is sigma referring to which output to choose from? Like we've got a lot of outputs, like by subtracting
So
caution.
no. So the thing is, yeah, here you should get the output of the previous step, right? The steps are not independent. Whatever you did in the previous step, you should use that, right? So if you see here, you are representing your D. Can you see my screen? Slide 8.
Yes, sir. Yes, sir.
So you are representing your difference of Gaussian as dxy sigma, right?
Yes.
So that dxy sigma we are using there. That dxy sigma we are using here. It's a function of 3 variables. Correct?
Uh, yes, sir.
I mean, you don't have to say yes. If there is any issue, you tell me. We'll discuss it.
Uh, so could you please explain this part? Like, so why are we
So you
estimating?
remember,
Uh,
okay, you remember the previous step, right?
yes, sir.
Slide 8. The output we got from the previous step was this dxy sigma, which is the change in the filtered image using a Gaussian filter sigma and using a Gaussian filter k sigma, right?
So you have to subtract the k sigma from sigma basically. When I write d x comma y comma sigma, then I have to subtract the k sigma part, not the other sigma value.
Yes. No, no, not k sigma. You're writing it as sigma, right? In the slides, it is given. You are writing your dxy sigma as your original Gaussian filter, and then you're scaling the variance of your uh, standard deviation of your Gaussian filter and calculating the difference between the two filtered images. Correct?
Correct. Yes.
That is your output at this step. D of xy sigma.
Got it.
Now we move on to the next step. Now, given this function, if there is a small change, delta s, where s is represented as some x1, y1, sigma 1, you basically expand this function as a small change in x, y, and sigma. You can represent it as a Taylor series expand. You can expand this function using Taylor series, correct? Up to some
Yes.
degree. Up to some degree. Here, degree is 2. Up to second derivative, you have expanded your function.
Yeah.
Now, to find the, like given a function, if you remember calculus, given a function, if you want to find the extrema, whether it is minima or maxima, what is the first step you do?
Take derivative and equate it to zero.
Yes, that is what we are doing here. Correct?
Yes.
So we take the derivative with respect to s, and whatever we get, uh, we equate it to 0, and we get the extrema, like our critical point. Our critical point is some of this form. Is that correct?
Yes.
Now, basically what you are doing is your low contrast point and points that lie on the edge. So basically you take those points. This is your extrema, right? So now you can use this as your parameter for your function and reject the key points which are smaller than some threshold. That is your localization.
I didn't get the last one. Like, why are we removing those points?
So now you have basically you have gotten the extrema, right?
Yes.
Now you can use this extrema to get the function value and reject the values which are lesser than some threshold, which they are calling, or the algorithm calls, low contrast point. You have S
So,
hat, right? You have S hat.
so, so when we have S hat, that means we have the maximum value in that output, like maximum pixel value.
Okay. Can you repeat that?
So, like at S hat location, we have the maximum value of
It
difference.
can be maxima or minima, right? It can be maxima or the minima. Don't know,
Hmm.
right? To
Hmm.
to know that whether it is a maxima or a minima, you need to get the second derivative.
Correct.
We are not going to that. We are simply rejecting the points which are smaller than some threshold or at that critical point,
Hmm.
which we are calling low contrast points. Okay.
Yes.
Now you have to do some sort of edge elimination also. First, you have removed the key points which are below some threshold. Now you can do edge elimination using the this something like Hessian. Like now you find the Hessian, right? So the next step, that is what you are asking, right? Whether it is a minima or maxima. This will tell you.
Yes.
Hessian will tell you. The second derivative will tell you. Correct?
Correct.
So now, instead of calculating, okay, you can calculate the Hessian and then you can use this trace and determinant to get some ratio. And based on this ratio, we reject the key points. So two steps we are doing. First, we took the extrema, we found the extrema, use the extrema to reject the low contrast points, and now we are eliminating edges using the second derivative.
So, what are low contrast points basically?
Low contrast point basically means that where the change in the intensity is small. That is what low contrast means.
Okay.
You don't need those points, right? So again, if I go to the same, I can find. Okay, see this. See this two images. Okay, let's say scale 64 and scale 4 we took. Let's say our sigma is 4 and k value we took 4. So not 4, 16. So we calculated the difference, right?
Hmm.
Now, once we have calculated the difference, there will be some points in the difference image which will have the very small intensity change, right?
Hmm.
You are simply eliminating those first using your extrema by calculating the extrema.
So basically, we need points which have a high difference. So those are the
Gradient,
points.
yes. Gradient gives you that only, right? Gradient is change in the intensity.
Correct.
So that is what we have done till now. Calculated the gradient and use that gradient to remove the points which are like below some threshold, where change in intensity is below some threshold, right?
Yes, sir.
And then we use the second derivative to eliminate the edges. That is how you get the edges also, right? If you go to the second derivative, you can tell the change in the how many, like the way we calculated the how we know based on the gradient and second derivative that whether there is an edge or not, right? So instead of doing that, we are calculating this ratio. Where is it? Yes. Right? So, 1 second. Here you have alpha plus beta divided by alpha beta. So, trace largest eigenvalue plus smallest eigenvalue. Two eigenvalues. Okay, so basically you are calculating the Hessian, and you are simply calculating the ratio of the largest eigenvalue and the smallest eigenvalue, right? And
Yes.
if you remember edge detection, at smallest and largest eigenvalue gives us the 1 second.
If lambda 1 is greater than lambda 2 or
Yes,
lambda 2 is greater than
yes.
lambda 1.
So it gives you the edge, right? Whether there is an edge or not. So
Yes.
you're simply using that information to get this ratio alpha by beta, largest and smallest value. That is why you are using this R to basically threshold whether it exists or not. And original Swift algorithm uses R equals to 10.
So basically, we're doing this step to only remove edges. That's it.
Yes.
Uh, but what's the equation behind it? Like, how does it remove edges?
No, no, that is what you are rejecting the key points. See the last step. Reject key points if your alpha by this ratio r plus 1 whole square by r is greater than a threshold. In the original Swift algorithm, they use r to be 10. So this is how they have rejected all the edges which are like not important, or you can think of it as they have rejected the edges which are not important, which doesn't matter for your key point. Because we are applying a threshold here, right? We are not rejecting we are not rejecting all, or we are not accepting all. If you don't reject, then you are accepting everything. Then this step doesn't matter, right?
Yes.
So now you think of it as something like this. In the previous step, we just don't calculate it for one sigma, right? One k value. We have multiple.
Hmm.
So next step also we will be doing it on multiple. So you will be getting multiple key points in your image depending on
Correct.
this value of k, depending on the value of the scale. Correct?
Correct.
And once you have done that, assuming you have got the key points in your image, we go to the next step, which is orientation estimation. Right? So now you want to achieve rotation invariance, that whatever view feature you get after the shift algorithm you apply, those are invariant to rotation. Whatever rotation you do, your features doesn't matter, like your features won't change. Right?
Yes.
So again, we use the this thing, the gradient, the scale of point to choose the correct image, and you compute the gradient magnitude. If you remember this thing, this particular slide in the previous step. Here, do you remember this? You can use image gradient to get the orientation.
Hmm.
So we are just using this, and also the strength, edge strength. We are just using these two steps to see here. Only difference is we are not applying it on the original image. We are applying on the image after applying a Gaussian filter. That is what the first step means. Scale of point to choose the correct image. We are simply calculating the magnitude and orientation. And then you basically create a histogram of gradient directions. This is the way to calculate gradient direction. This is the gradient direction, right? Theta of xy.
Correct.
So you create a histogram with the region around your key point, and then basically, I think you select the peak as the direction of key point. Wherever your histogram peaked, that is your key point, direction of your key point.
We only do it for those points where we found the key points, basically, not for
Yes,
all the
yes.
pixels in the
Because
image.
see, the steps are not independent. Whatever you did in the previous step, you have to use here in the next step. Right? So the way you calculate histogram is your histograms are weighted by the gradient magnitude and Gaussian function with sigma equal to 1.5 times the scale of key point. So in the first step you had the scale, right? K value.
Like in the first step.
Yes,
Yeah.
that you use in the second step for the differences of Gaussians.
Yes.
And now again you are using the scale, not the just the scale, you are using sigma equal to 1.5 times the scale for that key point.
So we're multiplying with the Gaussian kernel again for this step.
So see here, you have this Gaussian g of xy sigma. It will be 1.5 times k times sigma.
Hmm.
That you will use to calculate this I hat of xy, which will give you m of xy and theta of xy, and then you basically create a histogram of gradient directions within a region around the key point. And once you get the histogram, your peak is the direction of your key point, wherever your peak is.
How how to decide the area of region? Like how big should the region be by calculating the orientation of this?
Sorry?
Like how do you decide like how big the region should be by calculating the
No, no,
magnitude?
you have not calculated the region yet. You are just calculating the direction. Correct?
Yes. But how do you
Because
create the histogram for that? Like
you
including
can,
which
right,
point?
create a like you can create a histogram with the region around the key point. Now you can choose the region based on your understanding. Maybe Swift algorithm has some region. Okay, I think region is defined by. I think region is defined by this 1.5 times the scale of key point, right? Because you are applying a Gaussian filter over your image, right?
Correct.
You are not just applying your calculating your gradient magnitude and orientation using the I of xi. You are using I hat of xy, right?
Yes.
So Gaussian filter is defining the region. Then and there is another step which is saying that if there are multiple uh, peaks in your histogram, then you take another peak within 80% of max peak of histogram with different direction. So you can see here, this one example is shown. This is the original image, and this is the 832 DOG, difference of Gaussian extrema, with the directions given. All these arrows in the image are the directions of the peak, the key points. Correct?
Hmm. Correct.
And if you take the extrema to 729 key points after low contrast, like if you remember the second step, first we do the low contrast threshold, and then we move on to the ratio based on Hessian. So
Hmm.
you can see that the number of the key points are decreasing as we move on to different, like as we move into the algorithm. Correct?
Hmm. Correct.
So here you can see that. Can you see my cursor?
Yes, sir.
So near this window, there are this 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 7, 7 key points. As we go for the contrast threshold, we got only 3 remaining. As we move on to the ratio based Hessian based ratio thresholding, only 3 are remaining, right? So we,
Hmm.
okay, still 3 are remaining because there is no edge here. In this region, there is no edge here. So it will not remove any key point. And these are the directions for those key points. Correct? The
Yes.
arrows shown here are the directions. So what is happening here? We went from 832 to 729 to 536 key points in the image. Now, next step is key point descriptor. So now we extract local image gradient at selected scale. So remember, we have not let go of the scale. We are still using the same scale which we have used in the first step, right? Around the key points and form the representation invariant to local shape and illumination distortion. So now what we do is we compute gradient at each pixel in a 16 cross 16 window around detected key point. So like uh, this region, we'll take a 16 cross 16 window here and use appropriate levels to detect the key points. Downweight gradient by Gaussian fall function to reduce the influence of gradients. So simply you are basically applying the key point descriptor to find the key points. If I can find the example. So I'll give you one suggestion. Did you try to implement this algorithm?
Also, no.
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 My suggestion is that you try to implement. I think it is part of your assignment, grading assignment, correct?
I think in the assignment we had sober filter, so we did not have this.
Second, the last question was about the key point. One second, let me check.
It was Harris corner detection.
Oh, it was Harris corner detection. It was not the Swift one. Okay. So, see, these algorithms are all practical. If you have understood the theory, it is always better to apply it and see, because then only you will get a better understanding.
Yes, sir.
So basically, at the end, you will get the features which are like important features, which are not variant to scale, not variant to your shape, rotation, and not variant to your illumination. All those properties. That is it. Yeah, see in the slides already example is given that let's say you take, can you see my slides?
Yes, sir.
If you take this image of this book and same book is lying in some different orientation, your shift will be and with different scale also. In the first image the book is bigger than the in the second image, but both, if you use this shift method to calculate the features or get the features, it will still detect the same feature
This is
because
like the feature map of that book. Like it's the same feature map
yes,
book.
the same feature map, yes, because you are the way you are doing it, you are making sure that your feature is invariant to scale, translation, and rotation. Same goes for the color invariance or photometric transformation where your illumination is different. So you basically what Swift has done is it has used the basic methods of your computer vision for edge detection, the contrast detection, the Gaussian filtering to get the better features, which are invariant to scale, rotation, and illumination. And then it can be used to do image stitching or in different examples can be there. Okay, okay. So maybe I'll try to share the tutorial if I think this tutorial link is not working, which is given in the slides. I'll try to share the link with you guys in the discourse so that you can get a better, like you can apply and see.
Yes, sir. And so I also have one question related to video assignment in week one. Like it says that correlation is not associated. Why?
Week one. Which question?
Question number second.
Yes.
In in this point, correlation is not associated. Why?
So you can you remember correlation.
Uh, correlation.
So usually in correlation, what you are doing is you are taking. I think you are taking a filter. You are taking a filter and you are flipping it height-wise and width-wise, and then you are applying the operation. Correct.
Hmm.
So if you do the same thing, if you do A correlation B and B correlation A, do you think it will be associative?
No.
Will those two be equal?
No. So basically, it's like convolution, but the kernel is flipped from both
So if you
sides.
remember, you see the slide where professor has shown the how correlation becomes convolution,
Correct.
right? So if you remember that, if you apply the same step other way around, if you do A correlation with B and B correlation with A, do you think your answer will be same?
No. In this, like, what's the difference between correlation and cross correlation?
Okay, so here we are not talking about autocorrelation. It's cross correlation only. If this is not mentioned, then you're not taking the correlation between A and A. That will obviously be associative because there is no difference.
And so, in this, the fourth point,
Fourth point, let I be a given image. I star 2 pixel wise multiplication by 2 preserve contrast more than I plus 30. Yes. So as I told you, contrast is same thing. The change in the intensity, pixel intensity, correct?
yes,
So do you think I star two, like right? So I star two. If you do I star two and I plus 30, which will preserve the more contrast? Which will preserve the contrast?
times 2.
Times two, right? Because in the first operation you are just scaling it. You're multiplying every pixel with the same number.
Correct.
But in the second one, you're adding it, adding some number to a pixel.
So the difference will be same when we are plus 30. So
No, but your image can have a negative pixels, right?
negative is it's like
Value can
between
be negative.
0 to 255.
No, it need not be 0 to. Okay, I'll see this example and I'll inform.
Okay.
I'll try to get one example for this and I'll share it with in the.
Okay, sir. So in this seventh question, could you explain this high pass filter?
Sorry,
High pass filter.
it was part of the slides, right?
Yes, sir. It
So
just says that it allows high frequency pixels.
yes, it will only allow high frequencies.
Like, what does it mean? It means that it will only allow pixels which have intensity change. Basically, it only allows edges and blackens everything else. It doesn't mean that.
Uh, okay, wait a minute. Just give me 2 minutes. Yeah, I needed some water actually. Okay, so high pass filter basically means that it emphasizes details in the images. Basically, if there are some finer details or finer edges, it will basically emphasize those. So that is why high frequency will be allowed.
So finer details will mean edges in the sense because it will have
It can
high.
basically high pass filter can amplify your. Uh, so how to say that?
Like in fourth filter, we have both negative and positive, like in edge filter. So it will only allow the edges. But in all the other filters, there are first one is like negative average, like average filter, but elements are just negative. Second one is similar to box filter, and third one is also like average filter, like maybe can be say similar to Gaussian, but the middle value is one, so it will also give more weightage to the pixels close to uh, center pixel. So all the three above are low pass filter. They are only do averaging thing and align low.
So basically, high pass filter basically means that it amplifies your finer details in your images, and low pass filter basically means that it it smooth out the noise. So what will happen is, let's say you have a image which has a lot of noise. Let's say you add some salt and pepper noise to that image, okay, and you use this particular filter, the last filter, for to apply to that. What it will do is it will amplify those the noise you have added to your image. But if you use a low pass filter, it will try to remove those noisy pixels or noisy points. Is that, does that make sense?
Yes, sir. And so in this eighth question as well, why isn't the third option correct?
Eighth question.
Third and fourth option in this.
Third and fourth option is consider FT is minus infinity to F tau delta GT differentiation. Yeah, so what is happening here is you are taking a function, integral of some function, and you are taking a convolution of that with some function g. And this is not okay. The third part is not true, right?
It's correct. This one I think is true. Second one is false.
So this is just saying that you can shift that integral to the other part, and you can use the properties of integral to say that, okay, instead of taking the integral of f, I can take the integral of g of t and then represent it as capital G of t. So that is what this the third part is saying, right? So
Yes.
you basically, okay, so to get this you should write it, write this star is a convolution operation. You write what is your capital F, you write what is your g, which is g of t, and you write what is your convolution operation. You open this bracket up, and same thing you do on the right side, and try to see if you can get it from the left hand side or right hand side. You can get right hand side from the left hand side or vice versa. Okay. For all these four options, you do that. Only the first will not be able to. You will not be able to get.
Correct.
Someone else was saying something. Okay. Any other doubt?
So one more in graded assignment week 2. Question number 9.
Graded assignment week 2. I recommend. Which question?
Question number 9.
Yes.
In this, the last 3 points I did not get.
So the Sobel filter you can use to fetch the textual information, texture information. That is correct. Oh,
How, like,
obviously.
so Hubble is used to detect edges, but
If you read about the Sobel filter, it is doing that only. It can use to. I don't have the link now, but Sobel filter can be used to find texture information. Give me 1 minute. So, so one reason behind Sobel filter can help us find the texture information is because it is based on the gradient information. It calculates the gradient, the change in the pixel intensity. So So it can basically help us find texture because texture is usually textures are like there is a gradient difference between the pixels. That is why the Sobel filter can help us in finding texture information. And about the third point, large contrast changes are difficult to localize. Yes, because you see the it is a edge filter, yes, right. But it is based on it is actually calculating the gradient, right? Yes. So, other thing is the large contrast changes are difficult to localize because large contrast basically means the change in the intensity from one pixel to other pixel is high. So, localize means so you have this contrast, which is the pixel intensity change. Yes, correct, right? So contrast is already defined as a change in the pixel intensity. Now you are saying that change in the contrast can be localized. That is not possible because now you are going from like instead of looking at the 2 pixels, which is the localized information, you will be looking at a even bigger range, more pixels. right? For the change in contrast. Does that make it clear?
So, why is it difficult to
See, contrast is already localized. Now you are talking about change in contrast. Think about it.
So I guess large contrast changes are easy to localize. Like when there is a contrast change, be like dark and light, so we can localize it easily. Just like on the edges, there is a contrast change. So that statement is wrong because it's saying it's difficult to localize.
Okay, I misread the.
Difficult words.
Yeah, okay, I misread the. So local contrast changes are difficult to localize, right? I think it was part of your slides or something.
Yes, sir. It was given in the slide.
What else was there, Mehak?
the second point?
Maximally stable extremal regions are is only affine invariant. That is not true, right? We just discussed that.
So, what does this mean? Maximum stable streaming region in the final region.
Maximally stable. I think it was part of Swift, right?
Yes, sir.
See, the second point we do was the based on the stability, right?
So, the second step is this maximally stable.
No, no. Then we had this invariance about the orientation we estimated.
Okay, the fourth point.
Yeah. No, no. Third point, not the fourth point. So
Okay.
1 second. Okay. I think it was in different slide. Give me 2 minutes. I'm opening the slides. I think it was part two or something then. Maximally stable. Has to be block detection. Picture detector. Segmentation. Part 3. Which slide it was in?
I guess it was after shift.
Which slide it is in? Is it in second part 2 or part 3? Sit part 2.
It is in a slide title other feature spaces, and not this one, sir.
Oh,
But
it is in part 6 or part 7, is it?
yes, sir. Six, I guess. After the image segmentation slide.
Yeah. Not 6, then 7. Ah. So your question was, which of the following? This is not true. Well, it's not only affine invariant. Okay. Ah, so that is correct, right? That is what question asked.
It can be seen on this slide number
Not
14.
only affine variant. Which slide you are saying?
14, sir.
14.
Go below, sir. There was a chart for all the, yeah, yes, sir, this one.
Yeah. So it is region invariant, rotation invariant, scale invariant, and affine variant. And question say or option says that it is only affine variant, invariant, right? This one, the third from the last row, MSER. And now why it is, I think if you want, we can discuss it in the next live session. Why it is,
Sure, sir.
why it is not like why it is rotation invariant and all. We can discuss it in the next live session.
Okay, sure, sir.
Okay. So any, if there are no other doubts, then we can end the session now. I will stop the recording and live streaming.
So, one question, like there's a lot of content in week one, week two, week three. Like for exam, like what topic should we focus on?
Or your basic understanding should be there. That is all that is required.
Do we need to have a deeper understanding of all the variants of
No,
like
no, no.
SIFT and all?
So whatever is given in the lectures and slides, if you follow that, it will be fine.
So there's like a lot of content on slides. So
I can't give you any specific topic or content, but I mean, because I think that is what the issue was last time also. That first 3 weeks had a lot of content, and I mean, we can't do anything about it for now.
You can see the previous year paper, for example. You can have idea that which questions and all.
Yeah, that you can do. Try to see the previous year and previous term paper and see if you have any difficulty in any of the topics. You can clear your doubts in the discourse and live session.
okay, sir.